Testing, testing. Okay, today is just going to be a very quick stream covering a couple of individual problems. Okay. Yeah, let's maybe edit this to be private. Okay. Yeah, we're just gonna quickly go through the problems and give some quick explanations. Okay, so the very first one is the integral of x e to the minus x squared dx, and you're being asked whether it converges or diverges. Yeah, so with a problem like this, go ahead and see if you can get it to integrate to something nicely. So try out a u to u pair, right? You see this x squared here and this x down here, or x dx down here. That's a perfect u to u pair. So try that out, integrate it, and see what you get. And intuitively, whether or not you could ask yourself whether or not it converges or diverges first by sort of seeing what happens as you graph it. So at 0, it's 0, and then it sort of like rises up a bit and then goes to 0 in each edge, right? Well, okay, it's not very easy to say right off the top of your head whether this area here is finite or not. But maybe looking at the negative exponential, you know that negative exponentials decline really, really, really fast. And what's more, it's a negative exponential squared. So, you know, maybe that's your intuition. But work it out, and you should have something that integrates hopefully pretty nicely. All right. So number 2, you're being asked about 1 over x squared plus x, integral of 1 to infinity. So you can do this with partial fractions, but I think we should try to think about it a little bit first, right? So what we know about this is it looks a lot like x squared, but it just has this extra x here. So the point that I'm trying to get at here is maybe think about doing I think this is called a comparison test. Consider the integral 1 over x squared, which you know that when you integrate 1 over x squared from 1 to infinity, it's one of the classic integrals, right? From 1 to infinity, this is something very simple. 1 over x squared plus x just has a slightly larger denominator, so it's going to look just slightly less than, it's going to look slightly less than 1 over x squared, right? This is 1 over x squared plus x. So you'd expect that if this one converges, you'd really expect this one to as well, right? So go through with partial fractions, and I guess this is going to be a over x plus 1 plus b over x. Solve for a and b, and then integrate those. And what you should get is, I'd expect you to get some expression that looks like ln of, gosh, I don't really want to give it away. It's going to look like ln of, you know, some term in x up here and some term in x, you know, x plus something and maybe x plus something else. I don't remember off the top of my head, but it's going to be out to infinity. And you can realize that the limit of these two x terms are going to dominate, and the limit of those two is just going to be 1, and the ln of 1 is just going to be 0. But I saw some people trying to do ln of infinity minus ln of infinity, and that's kind of nonsense, right? My suggestion to you is to combine the fractions, combine the natural logs first before evaluating the bounds, because you can argue about the limit more rigorously that way, right? Just, it's going to bite you if you try to subtract infinity from itself. And that's what would happen if you kept them separated. So try that out, and hopefully it goes well. Hopefully get a nice clean answer. All right, we keep going. So if you go from 0 to negative infinity of z over z squared plus 4, 4 plus 4 dz, well, it's not immediately obvious what the u to u pair should be. Like, if this thing down here was like a z squared, right, we'd be in business because this would be a perfect u to u pair. But unfortunately, it's something to the 4th. So what we can ask ourselves is, all right, well, can we still use this z dz nicely as a, you know, as part of a u to u pair? And it turns out we can if we just choose to be a little bit, choose to be a little bit brave with our choice of u. So if we let u is equal to z squared, then du becomes 2z dz. And I sort of like reverse engineered this because I saw the z dz here and here. And that what motivated my choice of u in the first place. But the reason this works out pretty nicely is because then this just becomes a u squared, right? So this becomes the integral of 1 over u squared plus 4. And from there, this is going to look a lot like one of your known integrals. Look at some of your trig or inverse trig functions and see if you can get it to match up nicely with one of them, right? In particular, you might see something that looks like 1 over x squared plus 1 is the derivative of something in particular. So I would go ahead and try to work that out for yourself. Yeah, maybe the only other thing I'll say is you can, to get this to look like that, you can basically just pull out a factor of 4, right? You can turn this into 1 over 4 times, I think this turns into u over 2 squared plus 1. So maybe I'll just pull out the 1/4 in front, right? Very simple, just pulling out a fraction, really. But then this starts to look a lot like this inverse trig thing. So just look up what this thing is equal to and try to apply that over here. Yeah? All right, keep going. 4. Alrighty. So the next one, all right, is going to look like 11 minus x. Or we'll make up some other numbers, right? Let's make it like 10, and let's make it like a cube root or something. Yeah, so this turns into 0 to, I think, the point of interest, 10. And the idea here is, okay, near at x is equal to 0, this is just some finite number. But the issue is that as it gets closer and closer to 10, I think it's going to blow up a little bit to a vertical asymptote. And the question is whether or not it rises fast enough to make the thing diverge or not. And well, it's really hard to have intuition for things like this where you just can't visually tell how fast it rises. So my suggestion to you is to just go ahead and integrate this. Remember that you do know how to integrate 1 over x to the 1/3, right? Or just the cube root of x. You have a power rule for that. So look up that power rule, use it, and don't forget to chain rule to account for the negative sign. And hopefully this should all work out very cleanly for you. Right? And again, maybe a little bit of discussion is nice, but if you're basically, once you've figured out the antiderivative for this thing and you plug in the bounds, if it's something very clearly nice and finite, then you can tell that it converges, right? You also have to keep in mind that the integral over which you're integrating has to be continuous in order for this logic to work. But for this particular one, there's no issues throughout this portion. It's not like this thing has any vertical asymptotes in the middle. But yeah, go ahead, integrate that, plug in the bounds, and hopefully you should get something very reasonable and point you towards whether or not it converges or not. All right, we keep going. Yeah, this one over here looks something like 1 minus x squared from 0 to 1. And, oh no, square root of that. And this has sort of a silver bullet to it. This is another inverse trig integral. So look up in your textbook what your inverse trig integrals are, and just select the one that is the right match for it. Okay, so for the next one, they literally just give us like a series of numbers, and they ask you to come up with a common pattern. I feel like there's no point for me to really talk about this one too much, right? If it's like 2, 9, 16, like I don't want to patronize you and talk about this one too much, right? It's just look at the difference between them and start with, assume that n begins with n is equal to 1. So just come up with a general formula for these, and you should be good. I feel like there's not much I can say for a problem like this, right? They're just asking you a relatively basic series problem to get you primed for the harder ones later on. Right, so now for a slightly more interesting one. If you have a to the n is equal to like 7 to the n over 1 plus 8 to the n, and the limit, you're asked about the limit as n goes to infinity of an, you're curious whether it converges or diverges. Well, let's think about this really quick. Exponentials grow really, really fast. And of course, a larger base means it grows faster. So 8 to the n is going to grow faster than 7 to the n, right? But these are going to be just absurdly massive, absurdly fast growing integrals, not integrals, but values for each n. Well, I guess I should draw them as dots, right? They just go upwards like crazy fast. So the point I'm making is this one is going to be really insignificant in the limit. Which is to say, at some point, this one sort of just disappears, right? You can almost kind of like ignore it in the limit. So what you're left with sort of is 7 to the n over 8 to the n. Think about that. Think about that. Oh, by the way, this was supposed to be 7 to the n, and this one was supposed to be 8 to the n. And so then the ratio, ask yourself what happens to the ratio of the two. Right? So if it's 7 to the n over 8 to the n, what would it be? Because then 1 plus 8 to the n is just going to be something really, really similar to that, but a tiny bit smaller. Right? Gosh, I don't want to spoil these things too hard, but if you have another one like a is equal to 7 over n plus 2, I don't know, maybe let's make this, let's maybe just make this 1 over n plus 2. It should be pretty clear that it doesn't really matter for convergence or divergence. If you just have a constant up top, it really shouldn't matter. You know what I mean? Because a constant multiple isn't really going to change whether or not it goes off to infinity or not. So if you're being asked to take the limit as n goes to infinity for something like this, well, it's a little bit hard to argue about it directly, but what we do know is that the harmonic series 1 over n is very famous because it is known to diverge. Yeah, this 1 over n looks like, wait a minute. excuse me. Sorry, I thought we were talking about series sequences for a moment. Sorry, I thought we were talking about a series for a moment, but it turns out we're actually talking about sequences. So a series is when you add this up, and this one is very famous because the sum of this diverges from n is equal to 1 to infinity. You'll probably learn about that next week. Sorry, that's a little bit of spoilers ahead. But okay, the same still applies, right? You can still compare this to 1 over n, which obviously goes to 0 as n goes to infinity. But the idea here is if this here points for 1 over n, 1 over n plus 2, each one of them is going to be just a little bit smaller than them, right? Because this is 1 over n. How do I draw this? So the top layer is 1 over n, and then 1 over n plus 2 is just a little bit below them. So the idea is that if you know that 1 over n goes to 0, and you know that 1 over n plus 2 is just a little bit below it, but still positive, you can kind of say something about 1 over n plus 2, right? Like I heard a cute little analogy about this the other day. Like think of maybe cars stuck at a traffic light, or cars just on a road. The idea is that if you have sort of two cars, right, the 1 over n car and the 1 over n plus 2 car, and they're never allowed to crash, they're never allowed to touch each other, they have to, like, if one moves, the other one has to adjust its motion so that they don't crash. But the idea is if the car in front is sort of like in reverse, right, it sort of moves a little bit in the negative direction at each time step, right? In order for it not to crash, the other car sort of has to move a little bit away from it each time, right? And the idea is that if the car out in front is reversing and it gets arbitrarily close to 0, what can you say about the car below, the car behind it, right? I don't know. Maybe that analogy helps. Maybe it doesn't, but I think it's always good to try to use analogies when talking about math. Like this is ultimately very similar to the squeeze theorem that you've probably heard at least once or twice by now. But the idea is, well, maybe a different way to say it is if the top layer is like a ceiling, right? And the bottom layer is like maybe the floor of a room or something, and this is a wacky room, the floor and ceiling can adjust. Well, the ceiling's got to be higher than the floor, right? So if the ceiling is sort of lowering as you go along, the floor also has to get sort of lower as you go along too, in order for them not to crash with each other. Yeah? So the idea is if the ceiling goes all the way down to 0, or like very, very close to 0 in the limit, well, then you can sort of say that the floor has to as well, right? Anyways, I'm spending a lot of time on this because even though it's a relatively easy example of a series, I think it's really good to be very comfortable with the idea of squeezing, because a lot of students, start in the early series and sequence unit and think, oh, wow, this stuff is so easy, without ever really getting a strong understanding of squeezing or comparison. And that really sets them up for, I think, failure later on. So it's good to talk about the easy stuff a lot to make sure that you have a good foundation. Okay, but the next one is talking about some factorials, right? So if you take the limit as n goes to infinity of this, you can basically just write out the terms, right? Everything, so this down here basically looks like 4n minus 1 factorial times 4n times 4n plus 1. I'm just going to quickly write them out, okay? 4n plus 2, 4n plus 3, right? 4n plus 4. And I guess 4n plus 5. Wait a minute, is this right? Well, where did there get so many terms? No, sorry. Sorry. For some reason, in my head, I was thinking about the comparison test, which is something you'll learn very soon. I'm being very silly. There's just 2 extra terms, right? So there's 4n plus 1 factorial can just be written as 4n minus 1 factorial times 4n times 4n plus 1. So the idea is this part and this part cancel out, and all you're left with is 4n over 4n plus 1. And at this point, you can just kind of look at this, right? This is sort of a quadratic on the bottom, and as n goes to infinity, what happens to it? What happens to it? It's should be something hopefully is reasonable to answer for yourself. Okay, and for the very last one, yeah, I don't know. This should not really be surprising, right? How do you put it? So if earlier we already established that something that looks like 1 over n goes to 0, this looks something like 1 over n squared, which, again, by the logic of the squeezing, sort of goes to 0, or, it gets smaller even faster than 1 over n. So you can kind of tell me, you can kind of easily conclude the behavior of this 1 over n squared thing. And again, the fact that it has, a coefficient of 16 out in front of the n squared, and it has some other terms, those shouldn't matter so much, right? To argue about it rigorously, you can again use the comparison test to argue that those extra terms don't matter. But the sort of fundamental behavior here is governed by 1 over n squared. And it should be pretty reasonable to see why this goes to 0. Because for, again, the exact kind of a similar picture, if these dots over here are 1 over n squared, okay, the first dot at n is equal to 1 is the same thing, but then it gets smaller even faster. So if this thing over here approaches 0, then what can you tell me about these dots down here? Yeah. Alrighty. So last question is n squared e to the minus 7n. Okay. So we're trying to figure out, again, what the limit of this thing is as n approaches infinity. So let's just rewrite this as n squared times, or divided by e to the 7n. And intuitively, we know that polynomials grow kind of fast, right? That's a parabola. But exponentials grow so much faster than polynomials. That's something, that's something if you want to plug it into Wolfram Alpha or plug it into Desmos, you can or a graphing calculator, you can easily see for yourself that exponentials grow so much faster than any polynomial. Right? Any base greater than 1, any exponent with base greater than 1 is going to grow much faster than any polynomial. Anyways, the whole point of this tirade is to say, if you want to know the limit of this thing as n goes to infinity, well, unfortunately, it takes just a little bit of calculus or math, because you can see that both the top and the bottom go to infinity. So what you need is our old friend L'Hopital's rule. Yeah. So L'Hopital's rule will let you argue about this more rigorously. And remember, you might need to apply L'Hopital's rule more than once. But yeah, you can do that to figure out what the limit is. But again, intuitively, the denominator, the exponential, should grow so much faster than the numerator. So we'd really expect this thing to get small very, very quickly. Very, very fast. Yeah, if you don't believe me, just compare n squared and e to the 7n on Desmos, and look at how much faster one grows than the other, and figure for yourself that if e to the 7n is in the denominator, it's going to dominate and make the entire thing very small, very fast. All right, so that's that for today.